Okay, so welcome again. So what we'll do first part is go over the course logistics. So everybody is aware that this is the elective course, IDS 576, Deep Learning and Applications. So let me. So if you look at the course page, oh, sorry, I think that was the wrong thing. Sorry, I wanted to get into the student preview. So if I enter student preview, I assume that this is what you'll see. So there's a lot of links, but many of them are, just introductory, and you might have seen similar links in any of the other courses that you're taking, even last semester or this semester. So, for example, how to work, with this online mode of taking a course and so on. I think for us, the amount of content on this on this course site is quite minimal. So the most important one is the syllabus page, where there's a link to the syllabus. And if you click on it, let's see. Yeah, if you click on it, it directly goes to GitHub. Okay. Now, this may not be a very interesting way to see it, but I'll show you a couple of different ways to view this. And the reason why I put it on GitHub is because eventually what will happen is most of you will start working with Google Colab, and Colab, you can open these notebooks, and I mean, this is just a markdown file, so there's not much code here, but you can you'll kind of work with Colab in your projects. You'll start using Git as a version control system. You'll start using notebooks, this is a Jupyter notebook, and a Python notebook. So one of the reasons was that it's easy for us to get started with that. So syllabus is the first link. I'm going to get into the details of it soon. Next is lectures, and lectures is actually, if you it just says look at the syllabus, textbook, and materials page. Subsection, and you'll see that it's basically a collection of slides. Okay, and we'll talk about what are the textbooks and materials available for this course. Next is assignments and projects. So you'll see a bunch of links for uploading. Okay, so that's pretty much the key links on this page. And one more thing is Zoom. So Zoom, you'll see the meeting invites for every Wednesday at this time. So so those are the links. Syllabus, lectures, actually is redundant because syllabus will have the link to the lectures slides. Assignments and project is basically the location where you'll upload your assignments and appropriate dates, and Zoom is the link where you can get access to the meeting invite. Okay, so with that, let me actually go to syllabus page. So one way to view this notebook is directly, GitHub itself supports actually viewing such notebook files. So actually, if you open notebook files in, let's say, a text editor, you'll see a lot of extra markup, or basically metadata, which is not being shown to us when this is being displayed. You can also use a couple of other options. Actually, there's something called NB Viewer. Okay, so NB Viewer is a way to see any of these Python notebooks. Okay, so you'll see that your assignment submissions, for example, you will be able to use. You'll probably be using Jupyter notebooks or Python notebooks. Okay, they're just a way to interactively write your code in cells, and we can see an example pretty soon. So here, for example. Yeah, I think this is coming out. Repository. So actually, let me copy this link. Yeah, so this is just a viewer to view notebooks as well. I mean, whichever format you prefer. And the third option, so first option is just click on the syllabus page. You'll get to a GitHub link like this. Second option is use NB Viewer, which is a tool available from the Jupyter Foundation, Jupyter.org. And the third one is Google Colab. So you can just type collab.google.com or collab.research.google.com. You will need a Google account. I'm using my UIC account. You can use any of them. And here you can click GitHub, and So, um, so now, I mean, so it has found this particular, so it's just a, handy way to get access to GitHub public repository. So the repository where I'm using mostly syllabus and other notebooks is on this particular repo called DL notebooks. And we're going to talk about many of these. Okay, so right now I'm just trying to explain how to access syllabus page. You can just literally click and be done with it, but I'm just showing you a couple of things, NB viewer and collab. So here you can just click on syllabus here, and you should be able to see the live document, and you can actually edit it. So you'll see that this is actually marked down. This is not a code block. Okay, so this is what I mean by a Jupyter Notebook, places where you can write some code and or also text. Okay. But anyway, so let me actually come back to the simpler version. So what I'm going to do for the next few minutes is just walk over the key parts of this course. So this is a 4-credit course, and the objective is basically for folks who have done 572 or 575, one of those, or both, whichever, to see a few more techniques. Okay, a few more techniques in their tool belt when they work on machine learning projects, and it's complementary to them in the sense that some of the techniques that you see in those courses are actually very good, and they will get you most of the way for many conventional problems. Okay, conventional means when you have tables, basically, let's say databases and so on, you're getting data from there. Then probably the methods that you saw in 572 and 575 are sufficient. But more recently, and for many industries as well as companies, it's become important to work with a little bit of unstructured data. So one very prime example of that is text, literally reviews or customer support logs or transcripts or things like that, or product descriptions, for example. The second modality is images and videos. Right? So those are really, it's unclear if you just represent them as vectors or like a feature vector, then is that enough, or do you need to do more? And that's where I think deep learning brings in its own perspective and choices for models and so on to deal with the unstructured data sets. Okay, so that's where the crux of the core, the crux of this course is mostly working with certain types of data which are a little bit harder to work with with the methods that you've seen in 572 and 575. There's a second part to this course. The second crux is to also tie prediction to decision making. Okay, so which means, so a simple example that we'll cover later on is A/B testing. Okay, so when you're a decision maker and you want to decide whether you want to offer product A versus product B, how do you know which one to offer? One way to do that, one way to figure out which is a good decision to make, is to try out on a smaller segment of your customer base what is called a randomized controlled trial, which is exactly A/B testing. And so that's one example of decision making. But we'll see how we'll tie deep learning as well as any machine learning or forecasting technique to making decisions. Okay. So A/B testing was a very simple decision. Okay, do A or do B, or try A or try B decisions. But you can have much more complicated decisions. So we'll shift the focus a little bit and talk about how to tie machine learning with decision making in an algorithmic way, in an automated fashion. Okay. So it's not going to be simple manual decision making. So here's a list of. I hope everybody can access this page from Blackboard. By the way, throughout this course or any lecture, you can interrupt me anytime. If you want, you can turn on your camera. Mostly, you should try to keep yourself muted so that there are no extra noises. But you can interject anytime. You can also use chat feature. Actually, I am not able to see the chat by default, but yeah, use the chat feature if you have a question and you're a little bit shy in asking a question immediately. So there's a bunch of topics listed here in the syllabus page, and there's a much more expanded list you'll see on the lecture schedule, actually right below here. So there's a bunch of names for some of you who have not seen much of deep learning. There's a bunch of names, a bunch of acronyms, but we'll get into each one in detail and see how it's useful for certain class of problems. Okay. So the most famous, I guess, class of models are convolutional neural networks, and they are a good hammer to use when you have image and video data, and build on top of that as a example model to study from this course, and then you'll be pretty confident and you handle image and video type data. Similarly, you have time series type of problems. You can use what are called recurrent neural networks. Previously, you would have used ARMA or other time series models, a little bit more conventional. Similarly, if you want to work with text, recently in the news there are some names thrown around like GPT-3 by OpenAI, which mimics humans really well, and so on. We'll see what the details are of such technologies. Okay. Anyway, I will not get into the details of everything in the syllabus right now. There are few versions of the course that were offered by me before. There are video recordings for them as well. If you're interested, you can look at them. But certainly for these lectures for this semester, there's going to be video recordings automatically shared on the Zoom tab in your Blackboard. Okay. Finally, more, as I said, is online. So that implies that the office hours have to be online as well. So one convenient time slot is right after the lectures. So that is depending on how many students are interested, we can continue the Zoom meeting basically. We can also have appointments by email. Okay? And we'll have a separate, we'll set up a meeting time and use Zoom or any other, some other client as needed. There's a PA for this course, Ting Ting Ma, who is a PhD student in the department. So her and myself, we are the teaching staff for this semester. The schedule is somewhat dense. So it's only so dense in the sense that we're only meeting once a week, and the one meeting session is quite long. So that has the usual pros and cons of people getting saturated and so on. So do try to reach out to the teaching staff as much as possible to maximize maximize your learning. There are a few assignments. As you can see in the schedule, there is a bunch of points related to assignments due dates. And there's also a project component. So let me talk about those in a minute. There is going to be group work for this course. This is an elective course, so I assume everybody is interested in learning deep learning. Depending on your background, some of you probably are experts, some of you are beginners. That's fine. So there's going to be group work. So try to form a team of at most 2. You can certainly go solo. It is doable. It's not a very heavy course in terms of homeworks or assignments. So that's one of the components. Now, in terms of textbooks, we have a few textbooks. Actually, deep learning is a few years old now. It's a really it's a very comprehensive survey on deep learning techniques up to that point, up to 2016. There's also a very actively, I guess, iterating book called Dive into Deep Learning by folks at Amazon. But basically, it's also on GitHub. So there you'll see code as well as explanation next to each other, and code also in different variations. Okay, so there are some popular packages called PyTorch and TensorFlow for those who know it. And so this book has codes available for all, for 2 or 3 versions of these packages. Okay? And we'll talk about what these packages are actually towards the end of today's lecture. Okay. For the decision-making part, we're going to only look at a very small subtopic in the field of decision-making, which is related to making decisions, collecting feedback, and improving your decisions over time. Okay. And this collecting feedback business is somewhat new, I assume, for some of you. So we'll look into that, and the textbook for that is this one. Okay. But you don't have to read the textbooks to get the most out of this course. This is actually a trending topic in the past few years and even today. So things may change, new ideas may come up which become important, and so on. Lecture slides are a good starting point, which I'm going to go through the lecture slides pretty much in the lectures. So this lecture, today's lecture, and all the other lectures are available a priori for you to download and look at them. Software component, as I said, this course is mostly focused on deep learning techniques, and to choose a software language, we have to pick Python because that's where much of the action is, much of the tooling is available to evaluate models, try out models. For example, if you were not only looking at deep learning, but maybe other techniques, maybe R would have been a good candidate, or so there are some upcoming languages like Julia and so on. But we look at Python because that's where much of the very popular packages are actively being developed as well as supported. Well, now coming to the parts where there will be evaluation. So first is assignments. There are 4 assignments. Each one is about each one carries a weight of about 8 points. Each one should actually, the spacing between these assignments is quite quite liberal. It's 3 weeks between each assignment roughly, or more. So I would say as long as you get started soon, then you can as soon as the lecture covers the topic, then you'll be well paced to do these assignments, even if you don't form a group and work solo. Okay. Now, project is a big component of this course. That's because there's a lot of cool technologies that you'll see, and you are not a very sophisticated programmer. You can still use these building blocks to try something interesting, based on your own previous domain experience, for example, or other classes where you've done something using other techniques. You can switch over to using some of the deep learning techniques and so on. Okay. So those are the 2 big components of this course. Yeah, and grading is based on the project as well as the 4 assignments. And project, there's 2 timestamps. One is an intermediate check-in. So if we go back to after 7 lectures, I think on March 3rd, there's going to be a progress check-in where I'll meet with each individual or each individual group basically during class hours, and then finally in the last class we'll have some presentations. So depending on the number of groups and so on, just the timing of the presentation and stuff will be determined. And so sorry, this is not intermediate, but there's a final core which is due 1 day before that. So there's no exams for this course. Yeah, so that was quite a bit of details on the syllabus. So any questions?
Professor, I had a quick question.
Yeah.
I guess just generally speaking, when do you recommend we get started on the project, and like how big a percentage of the class is working on that project?
So it is a big percent, right? So if you see, it's about 60%, and I think there are 2 timestamps. So I think getting started on a project, on day 1, for example, today, maybe a little bit about you're not even exposed to even a single interesting deep learning tool. For example, I think by lecture 3, when we look at convolutional neural networks quite a bit, at that point, you can actually already start working with image-related problems. By Feb 3rd, you will see at least some exposure to text-based techniques, which are beyond, like PFIDF or bag of words and stuff that you've seen before. So with those 2 starting points, I think you can get started. So actually, what is expected is not that you front load your project effort in the first few weeks, but the project intermediate report would really solidify as a checkpoint where you would have a clear goal of, hey, these are the 3 steps in a project or a exercise that I'm going to follow through. Do they look good? And that's where the check-in comes in, and you'll get feedback from me and Ting on it. And much of the effort would probably be in the second half of this course. Okay. And that's by that time you will be pretty exposed to a couple of assignments, and you will see working with Python as well as PyTorch and TensorFlow, and you'll get a feeling for what's the right level that you should aim for your project, depending on your background and so on. But
right,
if you can certainly start earlier, yeah.
Right, thanks.
Yeah. Any other questions? Okay, so actually, I just wanted to quickly check how many of you are new to Python? Can you at least, so how many of you are new to Python, or old timers? Maybe add it on, just comment on chat so that I know that I have a sense. I could actually do a poll, but I don't want to take a tangent at the moment. Oh, some of the folks are new. Okay, so that's totally fine. I think you will learn Python on the way. So actually, one of the ways to learn Python is that you are kind of forced to. You want to learn those techniques, and I think the best way to do that is actually to to work on a very specific set of things. So here we will be looking at machine learning models, and so maybe towards the end of this class, and actually in the next class, we'll quickly go over some of the basics of Python. But I think at this point, I would also suggest getting a little bit, doing a little bit of self-study by looking at some of these notes. For example, you can click on these two. They just go over some of the basics of Python. If you have done some programming before, like Java, C++, C, or R, that is fine. We're not looking for efficient coding skills here. It's for folks who have done, who have decent exposure, do aim for good quality, programming. But folks are new, I think learning the syntax, and you'll see that it's actually a very good language for beginners who want to apply things in the real world rather than core software engineers. So it'll be a good experience, and that's where the tools that I suggested. So when I clicked on syllabus, I came onto GitHub. I think at some point you'll create a GitHub account. I think it's also suggested on assignment one. And another thing that you can start exploring is collab.google.com. Okay. So if you open collab.google.com, it actually opens an intro, a tutorial to kind of play around with it. So for example, yeah, so this is what is a REPL, basically read, evaluate, print loop. So it's basically so we'll see some basics of Python towards the beginning of next lecture. I don't want to consume time here, but you can execute code blocks. You can change the block to I think text. So this is just text here for this block, and this block is code. Okay, so anyway, I don't want to take a tangent here, but slowly you will start getting used to it, and you don't even have to install stuff on your machines. You just use Collab, and they provide, and they also let you use some GPUs. I think yeah, I think yeah, you can use a GPU or a TPU here, and as long as you don't excessively use it, you can actually use a GPU, and that's a graphic, that's a hardware accelerator useful for training the type of models that we'll be looking at this course. Okay. Okay, so let me actually at this point switch over to the slides. Okay, so the way I'll use it is I'm using a iPad and I'm using OneNote just so that I can annotate as I go over the slides. If you want, you can open the slides that are available. Right, you can just click on the one of these links. Yeah, lecture slides, and we'll reroute to Dropbox, where you can download each of the slide and slide deck and view it. Okay, so that's good. So yeah, I'll say, although it's not necessary that you need to know, before I get into the details, I was just looking at the chat and a lot of folks are new to Python. While you're new to Python, there is a little bit of ramp up with respect to usage of Python, as you'll see. In the first assignment, for example, there is a little bit of, you know, there's a little bit of, writing functions in Python and so on. I think that may be a it may be good idea to look at the assignment. Actually, you can directly, so here, if you use ND Viewer, you can actually go back to the directory structure and you can see assignments are directly linked here. You can also click them from the GitHub page. But if I click on assignment 1, you can see, for example, like a question which says, hey, write a function to compute what is called the logistic loss. Okay, and I'm going to describe what logistic loss is today. So it's not, and you'll see some other places where it's already written in some example codes that I'll give you. But what I wanted to say is that it looks like some of you are new to Python. It's a good time to go over the links here. A bunch of notes. I think one is from MIT and other is from Stanford, but doesn't matter. Whichever resource that you have, you prefer, I would say start looking into Python. And one way to do that is just try Google Colab and try different statements like NumPy is a numerical library that you can use. So by trying out this type of like a very interactive way of trying out, what's a variable, what's a function, and things like that, especially those who are super new, would be very useful, and it would be good if you get started on it this week. Although the assignment is not about Python itself, but it's good to get started on Python, refreshing your Python, or even getting started with Python. You can also go to python.org and look at the tutorials. There's going to be a quick start tutorial on getting familiar with the basics of Python. Anyway, let me come back here.
Professor, quick question. I know you mentioned that there is like so many slides out there from the previous years or sessions.
Yeah.
How different is that, or what is the reference point?
Yeah, so you'll see on the syllabus page there are previous versions, but what happens is because this field is trending quite a bit, as in things change. So for example, you will see that, you'll see that, for example, last semester, some of the lectures and some of the contents in some of the lectures were new. Okay, the most important one being GPT-3. Okay, so GPT is this very popular model which came into public media, mainstream media. It's able to write very coherent text. Okay, it's like an automatic text generator where you can ask any question and it'll create, let's say, an answer which seems very coherent. Okay. But what is the underlying technology behind it was covered last semester, and it was not covered before that, right? That's because these things came about in the past year and a half. So there's something called attention. Okay, attention is a generic term, but attention in natural language processing or state-of-the-art natural language processing or state-of-the-art text deep learning techniques means something specific, and it came about in the fall of 2018. Okay, sure, it's 3 years, but since fall of 2018, we could only incorporate it the past couple of semesters. So that's why, so all of their videos, some of the basic content will be the same, as it's somewhat stable. But what changes is the underlying tools. The first version was not based on PyTorch at all, but now we have kind of settled on PyTorch for the past couple of semesters and things like that. Okay, so if you feel like if you can do self-study, then not just this course, there are many other courses, including uh, uh, including some popular courses that you can take if you want to do self-study in deep learning. They will have videos and assignments and text, and the textbooks themselves that we are using in this course, they are openly available. You don't have to purchase them, so you can actually do self-study yourself. But the difference from with this IDS 576 version and the previous versions is that there is always about a 20% change in the material.
Okay, sounds good. Thank you.
Yeah. So it's 20%. It could be quite low, so you can certainly use previous years stuff if you want. And sometimes 20% can also be a lot. Okay, so I think I went over the course logistics. So the outline for today, for the rest of the time is as follows. So we have pretty much gone over course logistics. There'll be a brief intro to the course, which basically is like me trying to motivate why learning deep learning is useful. I think some of you already may have seen some really cool applications or demos of deep learning. For folks who have not seen it, maybe I can show a couple of demos when I talk about the course. The key things we look at in the course, and then the more detailed look will be a recap of classification as an example machine learning problem. And in classification, I think many of you know that you start with working with data, maybe look at columns and so on. So the data is an important piece. Similarly, your model that you want to pick is an important piece. For example, you can use a SVM, you can use a uh, gradient boosted decision tree, you can use random forest. Model is another choice. Generally, there's also another choice that you could make, which is the loss function. Okay. So with random forest and so on, you don't explicitly talk about loss functions, but if you think of, let's say, linear models, you could choose, let's say, a squared loss or some other type of loss, and so on. So we're going to talk about that. Okay. So that's what I mean by recap of classification. We're going to talk about how there's data, there's models, there is objective functions, and there's also a piece that I just mentioned, but we'll not talk about it too much in this course, which is algorithms, which is basically, for example, gradient descent-based algorithms to optimize the loss function. Anyway, those are the components of classification, so we'll have a quick recap of that. And the next thing we'll look at is what is called backpropagation. Okay. It's a interesting, I guess, thing to know when talking about deep learning models, because deep learning models are what you would say as they are differentiable, in the sense that they're models like linear functions. They have some nice properties, and when we get to backpropagation, I'll mention it. It's a good way to intuit about, how are these models fit to data. Okay, that's what we want to know from this part, backpropagation, that there is some underlying simple mechanical trick that we use to actually tune our models or fit the models to data. And then finally, we'll look at the first class of models, which are called feed-forward neural networks. They have been there for about 50, 60 years now. So we'll look at their description. But throughout all this, the objective is, for those who are super new, is to try to always connect back to what you've seen in, let's say, 572, or let's say, or an equivalent course, or 575. Okay. Actually, those who've done 575 last semester, you probably have seen much more complicated things than what we'll see today in this course. But yeah, always tie it back, and you can always ask questions during the session, and I can try to relate it back to what you've seen before. These are the outlines, and actually I also had a quick page that I wanted to show. Let me go back here. and that page is lecture details. So this is a a sister page. You can access it again from the syllabus page. Right next to lecture slides, there is a link. So this page actually tells you what the learning goals are. So it also gives you some extra links that you can look at. These are external links. So today's objective, before I actually get into the details, is to understand the key components of classification tasks. That's why I said data, model, objectives, and algorithms or optimization. We'll get into the detail soon. Um, relate business problems to machine learning methods, we'll just have a quick comment on the importance of identifying the right problem and identifying the overall solution rather than being wedded to a technology. So what we're going to discuss for much of the course is the technology, the deep learning technique. A collection of techniques. But it's not so much critical that you choose the right technique than to choose other components of your solution to a business problem. Okay, we'll just have a quick comment on that. And backpropagation is actually what is called chain rule. It's a term from calculus, and so we'll see how that that core building block which helps us tune our models, as I said earlier. And if time permits, we'll look at an example that we have, which shows how logistic regression for a 3-class setting, may not even fit, even if your data is just 2 dimensions. Okay, so let's say age and gender, and you're trying to predict, let's say, their salary. Not salary, sorry. Since there are 3 classes, something like education level or something, then it may not be enough. Okay, and we'll see a very synthetic example to show that, yeah, maybe some of these methods, the simpler methods, I wouldn't say simpler, what they are typically called shallow methods, but they're just techniques which are complementing deep learning. These other methods may sometimes not work, is what we want to show. Okay, the last point. So that's the goal for today. Yeah. Okay. So as I said, the key parts of the course, throughout the course. So first part is going to be deep learning. And the second part is the words we will use here are called online and reinforcement learning. It's just a terminology from the relevant subfield. But for, but the overall, umbrella within which these tools fall under is just decision making. In particular, it's called sequential decision making. As I was saying earlier, if you caught my word, it was a key word here is feedback. Okay, so there is a sequential nature to this where you try out some decision, you get a feedback on how good the decision was, and then you hopefully improve when you take the next decision and so on. So there's like some sort of a for loop. Okay, and so that's what we'll look at. So these are the 2 components of this course. So here's a quick comment, right? So whenever you see a business, problems in a business setting, they're all focused towards the key goal of that business, right? Which is value creation, whatever it is. It's the product, it's a service, and some of you have work experience, and so whatever whatever the org chart is, and whatever team that you're in, maybe a sales team, marketing team, or actually a development team, or whatever. At the end of the day, you want to work together with the rest of the organization to create value. And while doing that, you may be creating multiple products, services, and so on. And while doing so, once you've identified a problem which your clients have, for which you can create value and therefore charge money, you are now going to focus on let's say, the solution strategy. Right? And while you're doing that, there are many components that come into play to help make the solution a success. Okay, in the sense that solution actually addresses the need or solves the problem that the clients have. And the different components, for example, some that I've written here, are, how are you going to deliver your solution? May also be super critical. How are you going to work with data? How are you going to use data to derive parts of your solution which will be useful to your client. And the last part is, and we're talking about a machine learning style or machine learning based solution, or these days folks also call it AI. So AI based solution. And the last part is actually the techniques. So I would say, in my anecdotal experience, this is where I would say 70% of the effort is. This is where maybe 20% of the effort is, and this is 10% or less. In fact, even techniques, the techniques that you saw in 572 and maybe in 575, they may get you to most of the way in terms of giving a really good solution to your client, okay? Or as a part of your product. So deep learning, is not the first order thing most of the time. Okay. Certainly for some industries, let's say, industry or some business which really relies on working with videos or working with images, inherently, and that's the core thing. Maybe deep learning is super critical. But for a majority of the industries, well-established industries, which are now, being increasingly data-driven, I would say techniques are not super important. And even if they're important, deep learning itself may not be important. That's a 20,000 feet view of the lay of the land. But at the same time, it's not that deep learning is a fixed, fixed stagnant solution technique. It's a name given to an umbrella. So it's a name given to a collection of techniques that are constantly being improved upon, just like techniques which are rooted in classical statistics are also being constantly improved upon. The things that you see in textbooks are fairly mature, but things that you see still being developed on, for example, in the financial industry or the healthcare industry, if they're rooted in statistics, they'll still be being developed. And the same is true for deep learning as well. Okay. And so what I want to say there was that in some industries it may be good to learn deep learning because it will give you, it's evolving, and maybe it is a good starting point for more and more solutions. Okay. But I guess the important takeaway from this slide is that before venturing into a complex technique, and I would say deep learning based models generally tend to be a little bit more complicated. You would like to have a baseline, at least a benchmark. Okay, and that could be shallow or some complementary technique, like let's say a random forest based technique, okay, if you're doing prediction. If you come to the list of techniques, just focusing on that last cell from the previous slide, there are a bunch of techniques that you have probably seen, and folks who have done 572 or 575 have seen decision trees. You might have seen linear classifiers. You might have also seen examples like Naive Bayes classifier, SVMs. And what you'll see in this course is going to be neural networks and online and reinforcement learning. Although here it's actually related to decisions. There will be an underlying prediction or forecasting, subroutine or something which does forecasting. Okay. And so those are the two new things that you will add to your toolkit. Okay. And other things that you've seen which are not really related to prediction, but more like exploratory analysis, are things like clustering and market basket analysis. And you'll see a couple of unsupervised learning techniques even in this course, okay? But they will be related to deep learning. Yeah. So what I want to do next is take a couple of minutes to give a couple of examples, which I don't know if all of you would be motivated by. I'll try to augment it with a few videos that I have that show the promise of deep learning a little bit. Let's pick up. So here's one example, right? So let's say you're an online fashion retailer, or it could be also offline, like a brick and mortar fashion retailer, and you want to adaptively recommend products. Okay? And in the offline case, recommending products is as good as saying, put them on the front shelf, let's say. And maybe you have some estimation problems. For example, you basically want to estimate demand, And demand can be influenced by things like people substituting. Maybe they came for a pair of jeans and of a certain brand, and they didn't find it, and they took something else. Okay, that's substitution. Or they came to your brick and mortar store, online and offline. Uh, they came to your store and they saw a pile of 10 pairs of jeans for brand one and 2 pairs of jeans for brand two. And because they saw only 2 pairs of jeans for brand two, maybe they thought that it's selling fast, and maybe they want to pick it up. Okay, so maybe they're sensitive to stock level. So these are things that you cannot directly measure. I mean, you certainly measure sales that you're performing per each day and so on. So that so you want to kind of do something with it. So you can measure things, or your sales, or what customers say. Based on that, you want to take some decisions, which is hopefully adaptively make some recommendation decisions if you're online, or store arrangement decisions if you're offline. And it's not just those decisions. You can also tweak prices. So how do you get there, right? So you are making some measurements to what you want to, the business goal. There's going to be 2 steps, right? One is, maybe from those measurements, you kind of estimate something, for example, here in this case, demand, and then take decisions, which is subject to exogenous constraints, like business constraints. Like maybe you cannot stock too much inventory, or, brand A should not be displayed next to brand B, maybe because those 2 brands, have some contracts with you that they should not be displayed next to each other. So there's some decision that needs to be done. Here's a second example. So let's say you're an insurance provider and you want to improve the way you're pricing your insurance products. Okay, so maybe you want to customize the price to the client who wants to get insurance. Okay, and let's say house insurance. So for that, what you could do is manually check houses to know the different types of risks that the house would have. For example, which neighborhood it is, which neighborhood it is, and age of the house, and so on. But manually checking houses across each neighborhood, especially if you're a player, an insurance player, you would like to have lots of clients so that risk is very some sort of risk pooling happens. Instead of manually checking, you could do something creative. For example, you could fly a drone, which is quite something few folks do, especially in a couple of industries, not just insurance, but also, for example, agriculture. You can fly drones, you collect measurements, which are video footage, and from there you can run some estimation techniques, or basically prediction techniques, like classifying, whether there's a outdoor pool, segmenting house versus the background, let's say greenery, and so on. And maybe based on that, these are associated or correlated potentially with the right premium that you should be setting. So these are the decisions that you want to make. What is the insurance premium that your client should pay? But your measurements are in an unstructured format. Not just these. You could have structured measurements as well, but you want to put them together and make some decisions. Okay. And for both of them, I would say there's a need for. Okay, let me just go to this slide. There's a need for updating your decisions. Okay, so it's not like you take this, decisions of setting prices or figuring out your store arrangement, on day one and then forget about it. Right? You will keep revisiting your decisions. For example, what's the premium for next year? And this is where I mentioned there's this feedback loop. You try a decision, so you try a decision on day one or year one, and see how things pan out. And maybe in the next year you make updated decisions. Maybe your premium was high, so not many clients signed up. Maybe the risk estimates that you got were off, and things like that. Okay. Similarly, same thing with the fashion retailing example. Now, let's actually jump over to. Okay, let me actually go over to this slide. It's the same slide from before, except for one. This sentence is not correct. So let me come back to this, which shows both parts of the uh, example here. So those two examples were just, I was motivating them not about, they were not at all about deep learning. They were just about two different problems, one about fashion retailing, the other one about insurance. But that's where the business problem is. Like you want to, price your risk better. For example, insurance, you want to make more sales. From business problem, you want to boil it down to the actual underlying technical problem that, folks with machine learning background, folks with decision-making background can actually solve. Okay. And once you get to those folks can use some tools, and some tools that we'll study in today's course, or this course, this semester's course, are helpful towards those objectives. Now, for this course, the one of the key selling points is working with unstructured data. So, by structured and unstructured data, I just mean the following. Structured data means anything, there's no formal definition, at least in this course. Maybe there's definitions elsewhere. Structured data just means things which look like tables with columns and rows, and typically you'll find them in measurements, in the medical industry, or or event-based industry as well, like advertising, where you track click events and so on. Okay. Generally, there'll be a data warehouse where the stream of data will be put in, and then business analysts will pick up data by making SQL queries and things like that, and then build reports, or do some exploratory analysis, or build even prediction models. Okay. But even with structured data, although that's not the say the initial forte which made I guess deep learning famous, um, uh, deep learning still allows for something, and that is what is called embedding or representation of the categorical features. Okay, so one, I guess, example, as a teaser example, is related to text, right? So previously you would represent, let's say, a sentence using bag of words, where there'll be an indicator, like a 1 for if a word is present or not, and um, if some other word is not present, there'll be a 0 for it, and so on, like one hot encoding. So instead of that, you can actually do something uh, which tends to be empirically better than that, and that's called a better representation of those, let's say, words. Okay, and words are just like categories. Okay, like if you have a category like with state, state, there are 50 values. Instead of just one hot encoding them or something like that, you can actually have better representations for, let's say, the states of the US. We'll see this embedding or this word embedding when we talk about in a couple of lectures. Okay. Now, the more interesting data set, which is where I guess deep learning is a little bit more, is a first tool that you could choose, is when you have unstructured data. So images, which are tensors, so images which are just basically a bunch of numbers at the end of the day, but they are just collected in such a way that they look like what I call, they look like matrices, okay, or actually arrays, or three-dimensional arrays. And I'm going to talk about, and we're going to look at some of these objects in a few slides. Okay. So for images and videos, I would just classify them as unstructured data, and similarly, sentences, documents themselves, paragraphs, Twitter tweets, actually, uh, captions on Instagram, they're all unstructured, or even images on Instagram are also unstructured. This all would be, a good tool of choice to start to working on these would be some of the techniques that we'll see in this course. And what it actually brings to the table at the end of the day is it reduces feature engineering. So although you have a sentence or an image, even if you had tabular data, you would focus on which features are important, things like correlation plots, histograms, and so on. Instead of that, you can kind of skip some of those things, and not worry too much about feature engineering. So there's still some work to be done, but it's not the feature engineering that you would see when you work with tabular data. And the second part, so there's data variety, and that's one of the points that we'll touch quite a bit in pretty much every lecture in this course. And the second thing is about decisions. Okay, and I think I mentioned already, like things like how to price, how to, what to show, what to recommend. Um, and that's where, those are decisions, but sometimes you need to take decisions repeatedly, and that's the subtopic in decision making that we look at in this course, and not the whole of decision making, because that could be a course in itself. And these problems are called uh, learning on the go problems. So although you want to make decisions, since you get feedback, you can also learn that your decisions are bad. So you're directly learning your decisions are bad, rather than forecasting as an end goal in itself, like finding, and I'm going to disambiguate this when we talk about these. Okay, so one example here is A/B
Professor,
testing.
sorry to interrupt. We're all hearing some additional kind of a background noise along with your voice.
I think
Like
changing the mic.
sound.
I see a couple of people
Yeah.
with mic on. Let's see. Can you hear me fine? I can change my mic actually. Let's see.
We can hear you fine, Professor, but along with your voice, we can hear that buzz sound in the background.
Oh, is it the fan from my computer or something? Let me switch the mic. Now I switched the mic. It probably is an inferior mic though. It's the mic of the webcam that I'm using. So let's see if I can do something more. So sorry for a quick tangent. I've set suppress background noise to high. Can you still hear the extra sound that you're saying? The humming noise type
Now,
of sound?
I think now it's better.
Okay. So I have set, so you can also see in your Zoom settings that you can change the background noise, suppression to high, so high or low, whatever. So I've set it to high. If it still doesn't work, let me switch back to, I have a couple of mics. Okay, so we can switch between mics, and I have one more mic elsewhere. Next time I can change it. Okay.
Yeah, this is better now, Professor. Like after you
Okay.
did that, I think we can hear you better.
Okay. Okay.
Thank you.
You're good now, Professor.
Yeah.
Yes, no background noise. Thank you.
Okay. Thanks, folks. So yeah. So this was a summary of the, I guess, the higher level objective of the course. Basically, there's going to be data variety and there's going to be some decision-making components, and you'll see the decision-making components later on in the course, potentially lecture 8 or 9, around that time. We'll kind of start with video images first, and then get on to text next. Yeah, I think I've pretty much explained that part. So now what I want to do is actually, so what I spent about like 5 to 10 minutes talking about a couple of business problems and so on. So they were kind of disconnected from deep learning techniques, and rightly so, because as I said at the beginning, the business problem, backtracking that to a solution and then saying, hey, in terms of the techniques, let's use deep learning, is several orders removed. And you should always start with a benchmark, which could be a technique that you're already familiar with in 572 or 575. Okay. But if it happens that you're reasonably confident that, let's say, hey, deep learning is the right thing to use because, hey, we are working with images, or there's text, and there's some, let's say, pre-built models, and we'll see pre-built models and how to use them later on. Then deep learning is probably a good choice. So if you're at that stage, I want to motivate why deep learning is good. Okay, where you've kind of isolated that, hey, deep learning may be a right choice. And here are some examples which are examples which highlight the gains that deep learning techniques can bring to the table. The first one is a little bit older. This is from 2014. It's, vision just means images. So this used to be a problem that was held by academics or researchers. It's just a classification problem and was held under the banner called ILSVRC. It just means what this means here: large scale visual recognition challenge. Okay. So it's a challenge that folks were organizing in this community, vision or image processing community, or actually even you can also call them machine learning community, for years. And there was a big improvement around 2011, 2012. Okay, so actually the solution in 2011 was actually based on SVM, which some of you have seen in the previous course, right? So the big change was a huge improvement, a huge absolute improvement of 10 percentage points on classification error. Okay, so that was a big thing that really made many of the researchers, and these days, maybe hundreds of thousands of researchers work, take a look at deep learning techniques. Okay. So it's basically a classification problem on a huge collection of images. In fact, what this plot is only talking about one type of task, one type of challenge. So this visual recognition challenge had several subcategories or subtasks. The first task, task one, was the classification challenge, where you had to classify 1,000 classes of different images, different types of dogs, different types of cats, different types of sceneries, and so on, from about 1.5 million images. Okay, so and you're not pretty. So there's a little bit of slight, I guess, a sub point which is not critical at this point is that you're not predicting just one class. You're trying to predict. You see one image and you say, hey, this could be one of these 5 different things. Like, if it's if the image is of a certain breed of dog, as long as you predict 5 things, and as long as one of those 5 things is the same breed of the dog, you are actually good in terms of classification. Okay, so that's a minor point though. So that's a big delta, and that was achieved mostly because of an increasing access to GPUs that started even a little bit earlier, from like 2010, 2009, increasing access to GPUs and data handling, storage, which really made one of the themes which gave this incredible performance. Let them actually build that model, train that model, and that model eventually did really well compared to everybody else. Okay. At the same time, so that's great. And since then, folks have been applying deep learning to not just images, for many other things, but with many other things, there's always a caveat that it does not give, at least naively, if you use it naively, that the technique under the deep learning umbrella, they may not give you too much bang for buck. For images, it's proven, but for many other types of data or specific business problems, it may or may not, improve on, let's say, a random forest model that you've deployed, or a, let's say, even an SVM or a linear classification model that you've deployed. But so that's where I think a little bit of skepticism is, and I've written it here. Let's now jump to another example. This is an example of a deployed system as well, but not by Microsoft. So this is msn.com. It's a website with, when you open the homepage, it shows a bunch of articles that may be of use, that may be of interest to that particular user. Okay, so typically you'll have a Microsoft account, and they would have a profile of you, and based on that, they'll try to personalize what's being shown here. And so what to show here is actually a decision that you need to make. Okay, and what is interesting to you is probably a forecasting problem. Okay, for example, maybe you really like sports, or maybe you really like music. So there's both prediction and some decisions involved here. Okay, and the line between predictions and decisions is is a little bit blurry. Sometimes prediction itself could be a decision. For example, you may predict somebody may default a loan or not. And if the default probability is pretty high, you will not give them a loan. So the mapping from decision to prediction is not that different. But sometimes when you want to do something else, like manage your inventory, for example, in the retail fashion retailer case, you want to figure out how much how many more pairs of clothing, pieces of clothing of a certain brand that you want to buy. You want to, so that decision is not just dependent on the forecasted demand, but also depends on how much your budget is, and what are the lag times, and what else are you trying to showcase next month, and so on. Anyway, so here's an example. Here's what those folks did at MSN or Microsoft. They used user information. So they had some measurements. They had some measurements, and they used a technique, solution plus a model. They use the technique. So don't worry about what's in the circle. So there was a model, okay, decision-making model, or online, or it's a something which does online or reinforcement learning. Okay, and that model was able to produce a list of articles, and then they're shown to the user, and there's feedback. Okay, and that's what I said earlier, that we are going to look at a certain type of decision making where there's going to be feedback and hopefully scope for you to improve tomorrow. And so clicks are logged, and that feeds back into improving this model, and hopefully you show better and better things. And there are many other moving parts here. A lot of things related to setting up servers, creative things, figuring out articles, writing the articles themselves, and so on. And we'll talk about, and they saw a huge improvement in the engagement levels. Okay, how and we'll talk about those details when we get to this topic in lecture 8. Okay, lecture 8, or lecture 8. One, a next example, which hopefully gives you a sense of the progress in decision making driven by deep learning, is this landmark achievement back in 2016, where where for a specific game called Go, okay, it's very similar to chess. For a specific game, Go, Google, or basically DeepMind is the name of the company at that point, or they were merged. Google DeepMind produced an AI system, or an AI game playing agent, which it's a game playing agent, but internally it has some deep learning models. Okay, uh, so that agent was able to beat the then world top ranked player, human player, and before that, no AI system was able to compete with humans effectively, okay, before 2016. At least not able to beat top human players, which is not in chess. This happened way couple of decades ago, but for Go it was pretty recent, and that was enabled by advancements in deep learning, as well as in decision making. And a more simpler example is, this is actually also from almost about 5 to 8 years ago, is folks were able to, and this is actually a precursor. So this is an image of a Atari game, a bunch of Atari games. It's a really, these are just 2D games that you play. So this, when I say precursor, this is where DeepMind was able to show that they can build deep learning driven decision making solutions, in this case game playing agents, which can play these video games really well. Okay, and after this achievement, they moved on to this much harder goal, and they also, I guess, did really well there. Yeah. So so I want to give you a couple of more examples before we take a short break. And for that, let me. share my different window.
Hi, Teja. It's CJ.
Yeah.
I'm CJ, all of the
Hi, CJ.
MSBA program. Nice to be in your class. Is there a name that you prefer to go by, such as Teja, okay, or Professor
Yeah.
Teja?
No, Teja is fine. Yeah.
Perfect.
Yeah.
Okay, cool.
So thanks, CJ. Let me open a video that some of you might have already seen. So this is, I guess most of you recognize that brand symbol here. So this is a, oh, is it playing? Yeah. So this is self-driving. So this is a demo that they did. I think it's blurry because it's a very high-res video being shown on Zoom.
I don't think you're sharing the video. So, yeah.
Okay. Good points. That's what I was wondering. Okay. Sorry about that. Yeah, now you guys can see the video.
Yep.
Okay. Sorry, it's stopping and it's getting blurry. But basically, this is a demo of lane merging. A car which is not touched by humans. Going in an environment as crazy as this, a highway, and then getting onto the highway, getting off the highway, and parking itself, and so on. Okay, I think you can find such videos elsewhere. So, but what's the technology behind this, right? So, a part of it is actually the complex decision-making part that I was mentioning earlier. So there's certainly huge fields of engineering which are related to this, like electrical engineering, control engineering, and so on. But also, a big chunk of this is actually using the video to process the existence of roads, lane markers, signboards, and so on. Okay, so that's where deep learning comes in. So let me actually pause this. Okay, let's see. Yeah, so now I guess I've tried to share the whole desktop. You guys can see my screen, right? My desktop.
Yes.
Okay, so here's a different video. This is actually older one from what the previous one is. This is actually a demo in CES. Okay, so it's an expo for folks to demonstrate, cool, interesting technology. This is by NVIDIA. So again, nobody's in the car actually. This is trying to maneuver through the circuit by itself. Okay, and so again, the technology behind it is actually basically deep learning and online and reinforcement learning that we mentioned. So there's a lot more also going on, but there's also a good contribution by the techniques that also we'll see in this course. Okay, and just talking about vision. So I don't know how many of you have played this game a few years ago when it was popular. It's called Flappy Bird. And here's an example of a game playing agent which can play this game, similar to humans or maybe even better than humans. Okay. And here's one final. So there are others, but I don't want to spend too much time on that. So here's an example of being able to create new images. Okay, so this falls under the image related techniques, deep learning techniques, and also it's not a prediction problem. Here you want to completely synthesize a new image. Okay, here this is just showing how maybe the algorithm, the underlying model is trying to learn and hopefully generate new images. And here's a grid of like new images that it's trying to construct. Okay, and you can see some blurry mishmash of images. And this is actually a couple of years old. You will see much better videos of manipulating images or creating new images from scratch. Okay, and this is also something that we'll see I think around lecture. Yeah, okay, so I think we can take a 10-minute break and let's resume at 7:30. And if you have questions, I think I didn't. If you have questions, so if you have questions on chat, I'll answer them after we resume. So let's resume at 7:30. Okay, so let's resume. Yeah. So what we look at next is the specific details. Okay, so we'll start from scratch. So far, up to the first half of this lecture was mostly about motivating different applications and the larger context. Okay, and I won't repeat again. I think I've repeated several times where deep learning fits in the larger umbrella of solutions. And it's always good to have a holistic view of the business problem before jumping onto a specific technology. But in many cases, the technology has proven to be pretty good. And I think we saw a few examples right before the break. And so we'll start from scratch and pick up two things. First is we'll review a example machine learning flow, and that will at least give us a sense of which parts are going to change as we talk about deep learning techniques. And the second thing would be not a review, but a new concept, a new as well as an old concept actually. For some of you, you already know this as chain rule in calculus, but we'll revisit that through an example. Okay. So with that, let's get started. And if you have questions, I know this is the first class, so if you have questions, you can certainly use chat, or you can also stop me anytime. Okay. So this is the review. And if something is different from what you've seen before, do comment on chat and I can clarify. So let's pick classification as a prototypical example of a prediction task. Okay, there's also a regression problem, and also there are different types or variants of classification like multi-label classification, which is a little bit different, and so on. So let's not worry about all that. Let's pick I guess one category, which is this vanilla classification problem. Okay, so in classification, there are four things four levers that influence your process, okay, of building a classifier, right? So just to recap, what classification? You just want to build an object, in this case a classifier, such that for any new example or an observation or a feature vector, you should be able to give the right label that corresponds to it. Okay. So to design the classifier, you will need to just build this object, the one with the star mark. You need training data. You need to kind of consider different types of models. You may have to separately, or sometimes it's also baked in with the model. You may have to separately consider the loss function, which basically helps you determine what's a good model, what's not a good model for this data. Okay, and then finally, once you know what the loss function is, and what you can do then is optimize. Optimize just means, so if you only had like 3 candidate models, model 1, model 2, and model 3, then you can certainly compute some sort of a loss for model 1, loss for model 2, loss for model 3, and take whichever one is which has the lowest loss. Okay, but that's only if you have 3 models. I mean, generally, you will have an infinite number of models actually. For example, even for logistic regression or even for linear regression, the number of models is actually infinite because you can have many, you can have many coefficients, right, or many different values for the coefficient. So optimization is just a way to get to the best model by um, going from one candidate model to another candidate model to another candidate model. So, for example, if it's an iterative um, strategy, so as to get to a model which is really the best. Okay, this is just the implementation detail, the last point. Now, data, just a couple of comments about data. We have already discussed very briefly about types of data, structured, unstructured, and so on. Let's pick one example, which is from vision or images. So an image is essentially it's not always the case, but one representation of an image is basically some sort of a rectangle. It's basically a matrix. In fact, there will be 3 rectangles typically. Each rectangle corresponds to one of the color channels. Okay, so that's why it's called a 3-dimensional array. So this 3 rectangles or 3 matrices, okay, are just a collection of numbers. So each, for example, the first rectangle is basically a bunch of numbers, the numbers in here, and these numbers typically will have numbers between 0 to 55. Okay. So this is one way to describe what an image is. An image is just a collection of numbers, but in a set up in a certain way. Okay, with 3 matrices, one after the other, and each one may be representing a color channel. Okay. And the numbers can be between 0 to 55. It can be other numbers as well, but here's one way to represent the images. And some of the peculiarities or some of the characteristics of such data is that for the same object which is captured in the image, they can have so many different measurements, right? So the image can look different based on the location of the camera, location of the light source which is illuminating the object. If the object is rigid or not. Okay, it just means if the object is deformable, like maybe it's liquid or something else, or if something else is in between when you're taking the measurement of the object, like an image, or if the background is different, and so on. So the numbers will change, but the actual object in the physical world is the same. Okay, so these are some characteristics of such data that we want to either consciously consider them while building a prediction model. But let's come back to how we represent data, and this is going to be very typical, and we don't really need this type of representation too much. But generally, xi, yi represent the feature vector and the label. Okay, I subscript I just represents as a generic placeholder. Instead of x1, x2, x3, x capital N. Let's say we have 1,000 examples or 1,000 observations. Instead of writing x subscript 1 all the way to x subscript 1,000 as these feature vectors, we just generally representing that xi, yi with let's say curly braces or whatever. So I is equal to 1 to 1 to n. These are just notation. X just means the feature vector, y is a label, I is a generic pair, and there are capital N, maybe 1,000 such examples. Okay. A very crude, informal way of like considering deep learning versus before deep learning is that before deep learning, you would carefully construct this X. Okay. So this X, let's say it's a feature vector, you would actually construct that from the raw, from the original image. Okay, so given the image, you will do some transformation, some sort of operation on the image, so that you can, for each image, you would be able to construct, let's say, a 10-dimensional vector or a 100-dimensional vector. So that is what you would typically do before, I would say before deep learning, or actually, maybe 10 years ago. But these days, folks are not explicitly writing those transformations, from going from an image to an explicit feature vector. They're directly feeding a image itself, that collection of 3 matrices, or it's called a 3-dimensional array. And we'll see examples in the code, if not this class, next class. You can feed this directly into a model. So model typically is represented as an f function. Okay, so you directly feed an image into the f function, and typically these are actually functions in the programming language. So it will just be a function in Python, for example, within what is called a class. Okay, so but we're jumping 2 steps ahead. So that's what that is. So now let's recap what a model is. And model, as you guys have seen in 572 or 575, there can be different types of models. Some models are called parametric, where there are parameters. Many models have parameters. And there are some models which are non-parametric. Okay, like the k nearest neighbor is actually a non-parametric because there's really no parameters that you're extracting from data and keeping them to represent to be a prediction. Okay, so this distinction is not supremely important for us. This is just an example. I'm just trying to say that there are many different types of models. Logistic regression classifier or k-nearest neighbor are some examples of models. And we will pretty much focus on parametric, where SVMs, logic regression, random forest, they're all parametric models. And so deep learning models for in the next few lectures are also going to be parametric models. There's also something called hyperparameters, and these are things that that are extra parameters. Okay, and these are not exactly I guess these are just extra parameters, and they're called hyperparameters. And we'll see where, I think when we pick up a specific model, I think it'll be clear. I can make it clear what hyperparameters are. Okay? So these are just, think of them as an additional set of parameters, but they're given a special name because they're not optimized, or they're not picked in the same way as the first set of parameters. So just think of 2 sets of parameters is chosen in a different way. And some of you who have done cross-validation or something similar know that cross-validation is one way to choose hyperparameters. Okay, but we'll talk about that in a minute. So as I was saying earlier, we'll represent a model using this letter f. Okay, f is just stands for function, and a model is just a function which takes a feature vector and outputs a label. So this function certainly has to take a feature vector, which is, let's say, little x is the input, is a generic input. And let's say it has d dimensions. Let's fix all of this. So let's say it's 10 dimensions. Okay, d is 10. Okay, d is equal to 10. And w, so now I'm also presenting 2 extra inputs to this function. They're really not inputs, but they parameterize this function. Of course, if you change these parameters, it will be a different function. So you can either write it as extra arguments, or you can just write it as w comma p as subscript, or in any way. They just define this function. Okay, so so for those folks who know Python, it will be like def this model which takes input x as w times x plus b. Okay, so this is, so we'll talk about what this means. So for example, this here, as I said, x is 10 dimensions. W can be, let's say we're doing a 3-class classification, so then w can be 3 cross 10 dimensions. Okay, so because the output class, since we need to produce figure out one of, we need to predict one of the x is 10 and b is 3 cross 1. Okay, so what are these? So these are the dimensions. W is a matrix, and this is a vector. Okay, so this is it. This is how you define a model. The only problem is, what is W, what is B? You would not know a priori, and that's what we need to pick based on training data. Okay, once you pick them based on training data, then this is how you make a prediction. For any test input x, you just return wx plus b, but this itself is not telling the class, right? So if it's a 3-class problem, Wx plus p is just producing, what is it producing? It's producing 3 numbers. Okay, these are called scores. Okay, score 1, score 2, score. Okay, so 3 numbers. Okay, maybe let's say 10, 5, and -1. Okay, let's say these are 3 scores. So for let's say for given x, this function produce 3 numbers. The way you would do the actual classification is that you look at the scores and pick the index corresponding to the highest score. So let's say 10, clearly 10 is in this example. Then index for this is, let's say, 1. Then your class is 1. Okay, 1, or let's say the first index, let's say, corresponds to dog. Say you're doing a classification, cat versus dog versus fox. Okay, so let's say first index corresponds to dog, second index corresponds to cat, and third index corresponds to fox. Then these 3 scores just represent some sort of like a score. Oh, hey, this is probably a dog, or this is probably a cat, or this is probably a fox. Okay, the lower scores means the model is just saying, hey, this is not a fox. Okay, and so as I said, W, I think we've determined is 3 cross 10, and B is 1. Parameters W and B are parameters of this model. This is an example model. An example. Okay, and this is actually called a linear model. Okay, and this linear model is actually with a little bit more description on how scores get mapped to class labels. These labels, dog, cat, and fox, is actually the specification of logistic regression. And I'll show you in a couple of slides how this actually is exactly the same as logistic regression. You might not have seen logistic regression this way. You may have. It's a 3-class or a multi-class logistic regression. So generally, when people talk about logistic regression, they may be thinking about 2-class problem. Okay, binary classification problem. If it is binary classification problem, logistic regression is at least described in a slightly different way. But here, since it's a multi-class, 3 classes, or 4 classes or 10 classes, this is how the logistic regression model would look like. But the word logistic comes from somehow transforming this course to what there's basically probabilities. Okay, prob 1, prob 2, and prob 3. Sorry about the handwriting there. Prob 3. So there is there's a element-wise, not element-wise. So there's a transformation which goes from these 3 numbers to 3 other numbers, which happen to be between, let's say, sorry, not point. Let's say let's put 0.9, 0.2, and 0.01. Okay. 3 other numbers which happen to be between 0 and 1, so they cannot be beyond that range, and so that's why you interpret them as probabilities. Okay, and this transformation logistic transformation is complete this model description, that this is a logistic regression model. Okay? So a linear function like this, a linear function is which linear function just doesn't make x go crazy. Okay, if you had x times x square or x plus x square plus x cube or something, that's not a linear function. Okay. So that's an example of a model. Now, just what I described earlier, that you would pick the index corresponding to the highest score is what is described here. Pick the index. Pick the index corresponding to the highest score. Okay, that's how you generally classify. Instead of returning the full score vector, which is if 3 classes 3 scores, you could just return the what is called the argmax. Okay, so I think the reason why I'm using argmax here is that in Python there's a package called NumPy, and I think you guys should try working with NumPy. I think I demonstrated this at the beginning of the class. So in NumPy, if you have an array like 10, 5, and -1 like before, so this is called an array. It's called a 1-dimensional array because there's only 1 dimension. You can have 2-dimensional array, 3-dimensional array, for example, can represent images and so on. So you can do dot argmax, and you can get the index corresponding to the highest number. Okay, so that's essentially what argmax is. Index corresponding to the highest number. Okay, and this f as I said, returns a 3-dimensional vector in the earning example. So next, let's talk about loss functions. So is any question at this point? Okay. If there are questions, I think you can also put it on the chat. Even if they're basic questions, this is basically we can revisit some potentially confusing concepts from before, if they're not aligned with what I'm describing, from what you've seen before to what I'm describing right now. Okay.
Hi, Deja,
so
it's CJ.
Yeah.
You mind if I ask a question real quick? Can you go over the index real quickly one more time?
Yeah. So so index just means, so okay, so whenever you have a vector, so so this 10, 5, and -1, the first coordinate, so first coordinate, second coordinate, third coordinate. When I say first coordinate, that is the index of the element or the number 10. So the index of number 10 is in Python, it's actually 0 indexing. So earlier I said 1, but let's say 0 indexing, just because in Python you'll see index starting from 0. So index of this number 10 in this array is 0. Index of number 5 is 1. Index of number -1 is 2. So it's just like it's a position of the number in an array. That's what an index is. And .argmax tells me, so ultimately I need to do a classification. I need to, so let's say I'm building classify, which when, let's say, an image or some feature vector says whether that image is a dog, a cat, or a fox. So I have to say, hey, I can't, when I want to say dog, it's a string, right? Ultimately, in computers, it's just going to be a string. So instead of, so I want to say the class for my image is going to be dog if the 0th index is the highest. So 0th index has the highest value. So it turns out, let's say 0th index has value 10. That has the highest value among the 3 numbers. Therefore, I'll classify my input as a dog. If the first index is the highest, then I'll classify my input as cat. Okay, that's like interpreting my scores. So if you go back to my function, given an x input, it was doing basically so multiplication of numbers. Basically, it was taking x, multiplying it with a matrix, and then adding a vector. Okay, so let's not worry about matrix vector multiplication. At the end of the day, this will produce 3 numbers, okay, in this like vertical order.
Oh, yeah.
And from those 3 numbers, we need to somehow say which class it is, right? So I'm just saying that if the number, whichever number is the highest, is what I want to say the class is, and that's what and that time you're just using the notion of index to say that, indices to say that. Yeah.
Okay, got it. Awesome.
Okay. So let's go to loss function. So the previous definition was just a definition of model. Okay, but the model is parameterized by, in this case, I'm explicitly saying it's parameterized by matrix W and the vector B. But it doesn't matter. There's some parameter. Okay, the parameters are just some collection of numbers. Okay, at the end of the day, and you wanna now change these parameters so that this function is a really good, classifier. Okay, and how do you say which function is a good classifier? And to say that, you have to define what is called a loss function. Okay, so this is an extra function. This is like a second function that quantifies how good your any candidate classifier is. Because if I pick a random matrix here and a random vector here, that's also a candidate classifier, but it may be terrible. It may be classifying dogs as cats and cats as foxes, right? Just depending on this matrix W and this matrix B, right? So we want to pick which one is the best, and to do that, you need to define some sort of a quality measure for each of the classification functions. And the way you is using 2 parts. One part, this quality function will depend on 2 things. One is it's going to depend on your training data, and this is where training data is going to come in. And it's also going to depend on if you have a preference over some parameters or some, if you have a preference over parameters, okay? And that's through regularization. And I'll talk about that in a minute. So let's talk about first so what I mean is that loss function or this quality measure can be decomposed into two parts. One part just depends on data, and let's talk about that part now. That depending on data, it's just so all this loss function has to give me a quality measure or a score, right? Again, like some sort of, hey, this classifier is not good. This classifier is okay. So when you say good or not good, maybe good should receive. Since we're talking about loss, good should receive like almost a score of almost a quality measure of, and maybe not good should receive a high loss score because it's pretty bad. Loss is the opposite of it's like an opposite score, opposite scale than um, like reward, right? So instead of good models should have high rewards and therefore uh, low losses. That's what I meant. So a good model should have zero loss, for example. It doesn't have to be always zero, but a good model should have low loss value, and a bad model should have a high loss value. Okay, and that component of which depends on data is typically decomposed across the examples that you have in your training data. So if you have those 1,000 examples, so your loss over that component depends on loss over the first example, the second example, all the way to loss over the 100th example. Sorry, 1,000th example. Okay. So that in a short form was written as, so this is sigma. This is a Greek symbol. It's just short form, but you don't have to worry about the short. If you don't, it's fine. You can just write it this way. This is short form which says, hey, run I, index I is going from 1 to capital N, and the generic term there is Li. So this is like a sum over all these guys, which is exactly this. Okay. But anyway, loss is a function of this data component is determined by how does the function perform in each of my training example. So in each of my training example, any classifier should be able to classify correctly, right? So in my training example, let's say I have an image and I know its label is dog. So this function better produce the score for dog to be the highest, right? So this function should ensure that the score corresponding to the dog coordinate or the dog index should be maybe have the higher score ones, right? If it doesn't do that, then it's bad in terms of this example, which is supposed to have dog as a label, right? So, and here's here's an example. So let's talk about one example. Drop this. Let me not worry about the second example now. So here's the first example. So what is this example trying to show? How do I define the loss over one observation? Okay, so let's talk about the first observation. I said, hey, here's an image, and this should be a dog, right? So how do I, so and let's say I have a candidate classifier F, okay, which takes this image. So let's call this image X, and produces these three scores. And I want to say this this F is good or bad. Okay. So here is the loss function. It's called the cross entropy loss function. I think I'll write it, but it's called cross entropy loss function. So it's also called softmax. And the reason why you want to know this word is because there, in most packages, PyTorch or TensorFlow that we're going to see in the next lecture and beyond, as well as in the assignments, cross entropy is the word used for multi-class classification losses. Okay? And if you're doing binary classification, then there's a specific function like binary cross entropy loss. So anyway, cross entropy is the name of the loss function. So how does this loss function work? Here's the function. It's saying, so L1 is equal to minus log. And now what is this log? Let's keep it log to the base 2 or 10. Actually, log to the base doesn't matter, actually, although you have seen log to the base 10 most of the time, and maybe 2, a little bit rarer. The base is not really critical. Okay, you can might as well write 10 there. So log, and then you want to say probability of uh, probability of the true label because I know the true label. The true label is supposed to be dog. Probability of the true label given the image. Okay, image is X. Okay, the probability of true label is a dog. Let's so probability of the true label given the image. Okay, now what is this? Okay, so the way I wrote it in English, it may be a little bit confusing. But if you recall, the function is producing 3 scores, right? It's score for score 1, score 2, and score 3. Let's say score 1 is for dog, score 2 is for cat, score 3 is for fox, right? Remember, that's what the function is producing. And the function is producing that when its parameters are W and B, some specific values, okay? Let's not worry about the exact values of the matrix on the vector tape. Now, this of true label given the image, I'm going to write it in terms of these scores. Okay, how am I going to do that? I'll say probability of true label given image. I'll define, or I'll say that it is equal to e to the power, because I know the true label is dog, and I know the dog is index. Sorry, I'm again indexing it as 1 instead of Python indexing 0, but you get the idea. 1, 2, and 3. Let's say so. E to the power s1 divided by e to the power s1 plus e to the power s2 plus e to the power s3. The denominator is always a fixed thing. It's just take the scores, do an exponentiation of them, and add them up. Okay, so that's the denominator. And the numerator is e to the power s1 because I know that the true label is dog. If the true label was fox, then I would take e to the power s3. Okay. So this is how I would define the loss for the first observation, where I know that the image's label was dog. This is how I would compute the loss. So now you say, hey, can you again tell me what how are you scoring the model? Remember, the model F has parameters W and B. It takes input X and produces the scores S1, S2, and S3. So clearly S1, S2, S3 depend on W and B. Okay, they depend on W and B. Now, given W and B, I can say, hey, for the first example, your loss is actually equal to, because I know that it's supposed to be dog, it should be equal to negative log of e to the power s1 divided by this denominator. Okay. And similarly, for the second example, let's say it's a cat example. So let's say L2 should be equal to negative log of some different bunch of scores, because it's a different example. E to the power maybe s prime, instead of s is s prime, it's because it's a different number. But for the second coordinate, because the second has cat as the true label, divided by a different denominator, okay? Because there'll be different scores for that example. Okay? And similarly, you can compute losses for everybody, add them up, and that's a score for the model which has some specific value of W and some specific value of B. And the moment you keep changing W and B, you'll get different L data or these loss values, right? Is that clear? I'm doing a lot of detail here, but hopefully for those who know this, then it should seem fine. And for those who are new, hopefully it's clear how we are, given any model, like this is a model, we're able to score it for each training example and then add it up. Right. So what I want to again, yeah.
I have a question.
Yeah.
I want to know why you wrote S1 instead of S prime 1. Where I'm just confused with S prime.
Oh, S1, S prime. Okay, I was saying, so this is for first example. Let's say the first example, the scores were, remember, we were saying 10, 5, and -1, right? So the first example, L1, would be e to the power, because I know it's a dog, so it should be e to the power 10 by divided by e to the power 10 plus e to the power 5 plus e to the power -1. Okay.
Yes.
But for the second example, I didn't say what the scores were. Let's say the scores were, let's say, the cat is a true, second coordinate. Cat is the right answer. Let's say this is 2, 2, 5, and let's say -3. Okay, it doesn't have to minus, but anyway, 2, 5, and 3. Then this guy should have, sorry, this should be minus log of this. And this guy should have minus log e to the power, the s prime just means a different score. So it should be e to the 5 divided by e to the power 2 plus e to the power 5 plus e to the power 3. The prime just means it's a different bunch of numbers. That's
Got it, Professor. Thank you so much.
Okay, so the reason why I said this is, okay, so just to, close the loop, this definition of negative log, it's 2 or e or 10, it doesn't matter. Okay, don't worry about that. It's some log. Okay, there are different log functions, but negative log of this way of using scores is what completely defines a multi-class logistic regression model. So I don't want to now tease out and look at logistic regression and back to what you did in 572 or 575, but this is one way to completely define the logistic regression model and the corresponding loss function as well. So just to summarize, the logistic regression model is basically where the model is f of x is equal to something like wx plus b, and the loss, or L, at least the data component, is going to be some sum of L1 plus, and so on, where L1 is going to be equal to negative log of e to the power the right class. I mean, I'm just writing it in English, divided by sum over e to the power each class. Right? So each class will have some index, right? So if there are 3 classes, there will be 3 terms here, and the numerator should just be the right one. Okay, the number, the right class is 4. Sorry, this is a little bit messy here, but I hope you get the idea. So these 2 specifications completely say what, that this is a multi-class logistic regression classifier with the loss function. So the model is linear, and the loss function is such that these 2 together is just defines a multi-class logistic regression classifier. The logistic is exactly because of this e to the power and log business. Okay, I don't want to get into the details, but that's what a logistic function is. Okay. I mean, I think you guys might have seen logistic function as 1 by 1 plus e to the power x or minus x. Okay, let's say minus x. So these things look like that. Okay. If you just have 2 classes, you can somehow think about it that way. But let's not worry about it. Yeah. So I mean, the second example was about SVM losses, but let's not worry about it. Because I don't want to distract by saying, hey, here are 100 different things to define losses. I just wanted to motivate one way to say how good a model is. Okay, so if the model does well in terms of picks the right class in the training data, so let's say W and B are such that the score for dog is is highest, and in the second example, score for cat is the highest, then it turns out that negative log of, if remember, if the score is highest, e to the power that score will also be really high. Okay, e is like a exponential function, right? It just magnifies whatever the number is. So e to the power 2 is some value, e to the power 4 is going to be a huge value. Okay, it's not going to be 2 times 2. Okay, so it's not linear. Okay, so if e to the power, for the right class, if you get the score high, then e to the power that score is going to be high, and negative log of that is going to be low. Okay, so log of something, just somehow shrinks the number. Like log of 100 to the base 10 is 2, right? So it somehow shrinks the number, and negative sign just means that it's gonna shrink the number quite a bit if you get the answer right. Okay, so if you get the answer wrong, like if the model predicts that a score for dog is low, then this number is going to be low, and negative log of that number is going to be it will not shrink too much, which means the loss is bad. But I encourage you to do that exercise of, hey, what happens if I pick the right label? What happens if I pick the wrong label, as in the score for dog is low? Like if the score for dog is high and score for dog is low, for the first example, what is the impact on L1? Okay, just think about it, and we can discuss it right after the class if somebody wants to discuss. And you'll get the right intuition that for if the model is good, if the score for dog is high when it's actually dog is the right label, then L1 will be low for that model, and therefore, in a sense, that model is good. Okay? And if the model is good for all the examples, then the sum of those L1, L2, L3, L1000 will be low, and therefore we can, quantify that, hey, this model is good because it's classifying all the labels correctly in the training data. Okay? But I want to introduce the second component for a loss function definition, which is not related to data, which is called the regularization term. Okay? And you might have seen some variations of this potentially in 572 or 575, which is that sometimes, so you basically add an extra term, okay? And sometimes it has also a multiplier, like, here we are using Greek symbol lambda. So just think of this as like, 10 to the power minus 5 or 10 to the power minus 4 times some function which only depends on the parameters, okay, which doesn't depend on data. And what does the function represent? It represents our preference for certain types of models. Okay, like for example, if you have a certain preference that, okay, there's a matrix W involved there, and among all the choices of numbers that you can put in those matrices, I prefer matrices which look like a diagonal matrix. Okay, so that's my preference for that matrix, and that has nothing to do with the data, right? So if you want to express that preference, that can be expressed using this function. Okay, it's a regularization function. And why do people actually, why do they tap on this function? It's because they want to, impose some sort of domain knowledge into the prediction problem, while taking the right classifier. And there are a couple of other use cases for introducing regularizer, but let's look at an example. Actually, examples may be familiar with. Okay, the first example is called L2 regularization, where you just tack on something like 10 to the power minus 3 times, let's say it's a linear model, then it will be like beta 1 square plus beta square plus beta 3 square. Let's say it's a three-dimensional problem. Then it's just something like this. Okay, but in general, so don't worry about this beta things. These are just parameters of a linear model. If you had used this notation before, but otherwise drop the beta. Since you're using W and B, it's just the squares of the entries of the matrix or some of the squares of the entries of the vector, okay, whichever you prefer. Okay. So that's it. L2 regularization just means this. L1 regularization just means sum of the root values of the entries of the matrix. Okay. And if you have heard of what is called elastic net, it's just some sort of think of alpha as, let's say, 0.5. Alpha is 0.5 as well, therefore. And it's like, 50% use the L1 regularization and plus 0.5 times use the L2 regularization. Okay. So first of all, this symbol alpha, lambda, I would say if you're not very familiar with these symbols, don't worry. They just stand-ins, a generic stand-in for a specific value. Okay, some specific number, generally like a value like 0.5 or 0.9 or whatever, 10 to the power minus 3 or something. Okay. So these are examples of regularization. And we'll see one type of regularization a couple of lectures from now. It's called dropout in the context of convolutional neural networks. And it's going to be a little bit different than explicitly writing a function like this. Okay. But this is just a teaser. We'll actually discuss what exactly dropout is a couple of lectures from now. So what I want to do is now talk about three things we discussed. One is what is data, what is a model, and what's a loss function. Okay, loss function has two parts. The part driven, completely determined by training data. The part is not at all determined by training data. Okay, that was what the session was. Now we can put them together and now try to something so that we can figure out the best model. Because now we have this loss function which scores each model, right? And so we want to keep that eventually we get to a model which produces the lowest loss and therefore is considered the best, okay, based on the training data. And so for that, here is a block. here, we have a bunch of data and we have parameters. Okay, data parameters together determine my scores, my predictions for each training example. So I have put in generic training example xi, right? Like x1 would have 3 scores, x2 would have 3 scores, and so on. Okay, each one of them, will go into L, which is actually equal to L data plus lambda regularization, right? And L data itself is L1 plus L2 plus L, let's say, 1000. Okay. So this is how the block diagram is, and of how things relate to each other, right? So what we care about is this part, which is that we want to choose W and B. Like if any machine learning, the learning just corresponds to choosing W and B from training data. So this is the training data. Right? We need to find W and B. Generally, this gamma, let's say this is 10 to the power minus 3, something, it's called a hyperparameter. It is chosen based cross validation, okay, which is a little bit different than choosing the parameters themselves. So now that I'm motivated that, hey, we need to choose W and B, okay, that's the objective of optimization. Okay, so I know the loss function, I know the model, keep changing W and B, somehow figure out the best W and B, which gives me the lowest loss value. Okay, where loss is exactly defined as this. So let's skip this. This is a slightly different, instead of W and B, you can think of any parameter theta. Theta is again a Greek symbol. Um, so let's put, how do we find W and B or any parameter, okay, for that matter? And the way to do it is, and we're going to only focus on differentiable models. Okay. You may say, what is differentiable models? I think at this point and in this lecture throughout, we'll keep it informal. Differentiable just means they have first derivatives, or not just first derivatives, they have derivatives. Okay. What are derivatives? They are some there are some objects that I can describe better by. So let's say we have a function. Let's talk about a loss function. So let's talk about function. Like let's say z minus 10 the whole square. Okay, so this is a function. So this is f of z is equal to z minus 10 the whole square. Okay. Z is that input. Every input you give me, I'll just take the input minus 10 the whole square. Okay. So what when I say this function is differentiable, there is a derivative. So f prime, okay, which could be a function of z, is equal to 2 times z minus 10, right? So this is a derivative. It's like a rate of change of the original function. Okay. It's like, so the original function is actually, if you plot it, function of z, it's this value 10, this is 0, and this is f of z on the y-axis. Then it's like a parabola. Okay, so just I think folks who maybe this is a little bit is folks have done calculus long time ago. This may be like roughly in your heads, but f of z is basically a parabola, and f prime of z is a derivative. It's just saying how quickly does f change at different values of z. So when z is very far away from 10, f changes very fast, okay, because it depends on z. When z is exactly equal to 10, f, the original function doesn't change much because it's exactly at the bottom of the parabola. Okay? So that's what. So a function is differentiable when it has these derivatives. Okay, and this is called the first derivative. You can have a second derivative by thinking of how does the first derivative change, rate of change of the first derivative and so on. But let's not worry about all that. Yeah. So if we have differential functions, and you'll see that many deep learning functions or deep learning models are going to be differentiable. And because they're differentiable, we can use a very popular technique, which is very intuitive, also. It's called the method of gradient descent. Okay? So we need to kind of understand like what is meant by gradient. Okay? So gradient is nothing but is a bunch is a vector of partial derivatives of a function. So what is this vector? So if in this example, z was a single value. It was not a vector. So vector, remember, vector is a collection of numbers, like put together, one below the other, for example, like a three-dimensional vector and all that. In this example, z was a single number, so its partial derivative was actually a single number. Okay, but b happened to be a vector instead of so like think of a different example. If in particular a model, right, f of x with w and b, this is wx plus b, then let's think of its um, its gradient with respect to, because we want to let's keep x fixed and talk about how does this function vary when I change b or w. Okay, the rate of change of the function with respect to b and w. So for example, gradient of this function is denoted by this inverted like some triangle thing. Okay, it just is a shorthand to say, hey, the gradient of this function f with respect to, let's say, b. Okay, so with respect to some parameter. So let me pick the parameter b. The gradient of this function itself is actually is actually 0, because this is not above this function of b is just equal to b, so it's not, there's no rate of change with respect to b. But this is a vector of dimension, let's say, 3 cross 1. If b is 3 cross 1, this is going to be a vector of dimension 3 cross 1. Okay? That's what I meant by a vector. Okay, but let's not worry about vector gradient for now. Just suffices to say that if the models are differentiable, like something for which I can derivatives, people can figure out derivatives, then there's a way to optimize. There's a way to figure out the best model. Okay, there's a way to optimize the loss function. Okay, and how do we do that? I think I mentioned that it is an intuitive technique to optimize the best model. And let's ignore all the notation from previous slide, and let's talk about what is intuitive technique. Okay, the intuitive technique is as follows. You start with a initial candidate model parameters, let's say w naught b naught, okay, which just means you start with some matrix. Okay, let's say we were using 3 cross 10 and 3 cross 1, right? That was the running example from before. So some numbers, okay, 0.1, 0.5, some 10 such numbers, 2, 5, and 10 such numbers, 3, 2, 10 such numbers. So 3 rows and 10 columns, a bunch of numbers. I start with some arbitrary numbers, 0, 1, 5, some bunch of arbitrary numbers. Start with some choice, okay? And then what you do is you find the loss value for this model, because once I specify w and b, there's already a candidate classifier or a candidate model. For this model, using the training data, I can tell what the loss value is, right? It could be high or low depending on the numbers here. And then the intuition is that we're going to change from W0, B0 in an iterative fashion to W1, B1. So we'll go from W0, B0 to W1, B1. So another pair of matrix and vectors, another pair of numbers, such that what we want is that the loss value for the, with the hope, with the promise that the loss value for this new pair of parameters is going to be smaller. Okay? Remember, we want smaller and smaller loss function. Low loss function implies better and better model. Okay? So we want to do this change, okay, and that's where all the intuitive trick is. Okay? So we want to do something iteratively. We want to go jump from parameters to parameters, and this jump is such that at the new set of parameters, the loss value is lower. Okay, and this jump is achieved by using the gradient information. Okay. So we'll talk about how do we go from W0 B0 to W1 B1. Okay, and we'll do that by using gradients. Okay, or there's some new quantities that we can compute, which are gradients are nothing but this vector of derivatives, and will let's say we can somehow compute the gradients. Okay, then how do we actually use it? Here is the let's skip the first 3 points. So let's pick the first couple of points. Let's focus on these two. Okay, 2 points. What we do is, we have W naught and B naught. Okay, we computed the loss with respect to them. Okay, we can compute the loss with respect to those parameters, right? This candidate model. What we can also compute is this gradient of this loss with respect to W naught. We can also compute the gradient of this loss with respect to B naught. Okay. So this is just a short form, as I said, inverted triangle. But this is just like how quickly was the loss change when I change the B or the B vector a little bit. And sorry, this one is the one which says how quickly does the loss change as I change B a little bit. And this one says how quickly does the loss change if I change the matrix, a little bit, like shake the matrix. Basically means change the numbers here and there a little bit. Okay, that's what the gradient does. And turns out if as I said, if B naught is 3 cross 1, then the gradient is also 3 cross 1. Okay, this crazy looking symbol here, just it's a stand-in for gradient, is also 3 cross 1. If W naught is 3 cross 10, then this gradient is also 3 cross 10. Okay, in the sense that it's also a matrix. And so then this update rule that I said, going from previous W to the next W is as simple as adding. In particular, it's actually subtracting. Okay, it's just take the previous W and subtract subtract a gradient, but multiply it with a small number. That number is called the learning rate. Okay, it's just a name, has different motivations, but it's just a number that you can pick a priori. Okay, it still works. Okay, some number like generally a small number like 0.1 or something. And you can have potentially different numbers. So that's why I wrote alpha and beta as standing numbers. You can just think of them as like a 0.1, and beta is also like 0.1. So that's it. That's gradient. It's called gradient descent. Okay, it's because we are trying to minimize loss function. Remember, if you look at the parabola earlier, this one, right? So let's actually pick this example. Let's say we start with Z naught, okay, some value. So I thought, so let's say Z naught is 20. Okay, so let's say Z naught is 20. And what I want to do is minimize, just think of this f of Z as like a loss function. Okay, it's positive and it has a like a minima or like a lowest value when Z is equal to 10, but I don't know Z is equal to 10 a priori. Okay, what I'll do is take Z naught is equal to 20 and then try to find Z1, which is equal to Z naught minus some as I said, some multiplier times the gradient of the function with respect to Z. And that's exactly, the gradient of the function with respect to Z is exactly equal to f prime of Z. And we know what that is. It's actually equal to 2 times Z minus 10. So we can actually say, hey, this is equal to Z naught, which is 20 minus 1 by 10, that's 0.1, times 2 times 20 minus 10. Okay. So the Z1 is equal to 20 minus, this is what, 10 times 2 is equal to 18. Okay. And you can see that at 18, that loss value, or the f of Z, is lower, right? So that's what gradient descent is. Okay. And that's the core for the optimization. So let me, and there's a picture here illustrating the same thing. But if it turns out that your loss function is all over the place, then you may not get to the lowest value. Okay, depending on where you are, you may end up in a different minima, quote unquote, or a low loss value. Okay, With that, I think I'll skip the hyperparameter tuning part. It's actually related to cross validation. Actually, the reason I'm skipping it is actually in deep learning, most people don't do cross validation. So, but you must have done cross validation in 572 and 575 potentially. So that can be used to tune any other choices other than the intrinsic choices of the model, like W and B. If you want to choose something else, like how much is the regularization, or if you want to pick features, feature selection or whatever, then you can do cross validation. Okay. Let's actually stop at this point. And let's see if there are any questions you can ask now. And I'll also be staying beyond the lecture hour now. So if you want to ask questions later, I'll be speaking up. So to summarize, since we have like less than 30 seconds, what we've done today is just a recap of a classification pipeline. What we saw is data, models, objectives, which is the last function definition, and a technique to objective. Okay. Now, for much of the remaining lectures, we're going to focus on data. We're going to keep changing the data, images, text, and so on. And we're going to focus on models. Okay. Mostly the last function is going to be that cross entropy loss that we saw if it's a predicate classification problem. And we'll probably not be touching too much on the optimization, although everything underneath whatever we do in computation, for example, using PyTorch or whatever, using Python, when we train our models, we are actually doing gradient descent. Okay, and it's a core part of assignment 1. It's a core part of assignment 1, just to get a feel for, hey, this is how you would optimize differentiable models. Okay. But assignment 1 is a little bit far away. I think it's not. It's like a couple of weeks from now. So we, in the meantime, we'll get more and more familiar with these concepts. Okay, thank you, everyone. I'm gonna stop screen recording now. But if anybody has questions, you can ask right after.
Professor, I'm Vanessa. I have a question.
Yeah, let me just.